In this video, we're going to look at some stuff about the derivative. The main concept we'll tackle first will be how to understand what the new derivative function is. We'll also look at a few other things as well. This is a function, which is a very simple derivative. Being the function is made of straight line pieces, we can actually calculate the derivative at most of the points. We'll see that when we're in the region to the left of -2, the slope is constantly equal to -1. Between the points of -2 and 0 for x, the slope is constant 1, and to the right of 0, the slope is constant of -1/2. So the derivative function will be constant -1 to the left of -2, +1 between -2 and 0, and -1/2 to the right of 0. I will mention, though, that we do not have any values for the derivative at -2 of 0, because the function is not differentiable at this point here, and we'll see why in a few slides. This function is much more like the ones we'll actually encounter in class. We'd like to be able to turn a function like this into a derivative graph. In the previous slide, going back a second here, we were able to turn a straight line graph into another straight line derivative thing, and we had straight line graph here turned into a straight line derivative. This example is curved, therefore the derivative is always changing. We can do some very simple analysis here. This breaks it down into some nice simple steps. We first look at the points on the graph that have 0 derivatives. We have to look at the tops and bottoms of valleys. So at those points, we see clearly we should have the function have a 0 derivative. So we put for the derivative function to have values that are 0. The values you see shown here in what I'll call orange. So those carry over to the graph here on the right side as well. We'll notice then that in this region here and this region here, the graphs here and here are increasing. Because of that, the graphs here and here are above the axis. Again, if the derivative, say if the function is increasing, f prime is positive. Conversely, on the regions here and over here, we have that the function is going downhill. If if f is decreasing, f prime is negative, which we see it being below the axis here. So again, going this one more time, the two regions, both here and here, where the original graph was increasing, the derivative is positive. We don't know the value of it necessarily from this simple analysis, but when this graph is going uphill, this function is above the x-axis. When the graph is going downhill, both in this region here and this region here, the graph is below the x-axis for the derivative. Again, to make this clear, the top is f, the bottom is f prime. Or, I'm sorry, g and g prime. I'll mention just a simple typo. These statements here are true for f, g, or any other function you're talking about. This is another example here. Going through the same analysis, I find the 0 to be right there, which gives me the value here. But there's also kind of an obvious issue with the point that's here and here, where the function kind of does some crazy stuff. If I look at what happens to the function between the known 0 and this asymptote here, the function between there and there, which I'll highlight here in green like they have, this function is always going downhill in that region. So down here on the graph, that will be a negative region down there. I also have decreasing functions here and here, and you notice the functions in the derivatives portion are negative and negative. The fact that they get close to 0 along the x-axis is because their slopes approach 0 as they go further and further out. And we might see that in another video in the future. The last region we haven't drawn is the one I can sketch in here as blue. On that region, the graph is increasing. So now the function derivative has to be positive. So again, the green on the upstairs for this function, f, not use that color, use orange, f, and f prime at the bottom. When f is increasing, I have it shaded blue, therefore the derivative is positive. When f is decreasing, I have it shaded green, and the derivative is negative. Notice that we have zeros at the spot where f, what we're going to call, is stationary, and the derivative is discontinuous where the original function was discontinuous. The next theorem tells us something about the connection between differentiability and continuity. If f is differentiable at a, then f is continuous at a, which seems pretty straightforward. However, it's much more used in the contrapositive version of this, that if f is not continuous at a, then f is not differentiable at a, because if it was differentiable, it would have to be continuous. So this is a situation here where this graph is not continuous at a because the limit as x approaches a of f of x does not exist. And since that means that the function is not continuous, the function is not differentiable, and we can write down confidently that f prime of a does not exist. But again, that theorem in another version is that a function, if f is not continuous at a, then f is not differentiable at a. This is a slide showing some different ways for functions to not be differentiable. As I approach the values of a from the left-hand side, the slopes are approaching the slope of the line. Oops, sorry. Sorry again. Approach the slope of this line here. But if I walk in from the other side, the slopes approach the slopes of this line here. So we would have two different values competing for what the derivative could be. Should it be the slope of L1 from the left, or the slope of L2 from the right? Because these two slopes aren't the same, the two lines aren't parallel or coincidental, we would say the derivative does not exist here. This is another point, another way the derivative can fail to exist. These two functions, as I walk in from either the left or from the right, approach a vertical line. Because of that, we get these two situations down here that they even appear going off in two different directions, where one is a positive infinity, one's a negative infinity, but it is still the same tangent line. Because of that, this very somewhat simple function does not have a derivative at the origin. This one, being even a simpler function, simply being the cube root function, has the same situation. It has a little bit nicer situation here that as I walk in from the left or from the right, I approach positive infinity from both situations. But we don't want to say the derivative actually equals infinity, so we simply say that then this does not exist. This slide simply sums up what we saw in the previous ones, how functions can fail to be differentiable. The three main ways it can happen: if the function is not continuous, if it had a corner like we saw with the L1 and the L2, or if it has a vertical tangent line, which we saw in two slides, 3.20a and 3.20b. This one goes through the different cases of it. Again, at the point of -2, the function is not differentiable because f is not continuous. That's also true at x equals +2. Now, at -2, it was not continuous because the limit didn't exist. At x equals 2, it was not continuous because the function doesn't exist. The function is also not differentiable at x equals 0 here because it approaches either a corner or a vertical tangent line. It's not overly clear from the picture, but there's obviously some very big issue happening right there. This one goes through some more examples. We have another crazy function that has some issues. At x equals -2, once again we have a discontinuity in the function, and therefore that this statement is true, that g prime -2 is undefined. On this region here, the function is constant, and therefore the derivative is constant. Oops, I'm sorry, I misunderstood. This is the graph of the derivative of the previous function. Because we had the function was not differentiable at -2 or at 0, this is actually what you could get if you analyze the derivative of this graph. We knew it had issues at -2, 0, and 2, which means the function is not defined at -2, it's not defined at 0, and it's not defined at 2. But look at this graph here. I do my same kind of analysis with colors, It's increasing here with constant slope. It's increasing here with a slope getting closer and closer to 0. It's decreasing here and decreasing here. So on the next slide, I'd have that positive constant here. I'd have that decaying positive here. I'd have the two negative values there. Again, I'll mention that these get more negative here and here when this graph gets more and more negatively steep. As always, please contact me with any questions, and I will let you know if I can help you. Thank you.